Okay, this is chapter 8, and we're going to be talking about bonding, and I think that you're going to find that this is not very different than what we did in Honors Chem. Just a little bit more with some of the exceptions and just a little bit more depth, but pretty similar to what we've already learned about. So there are three basic types of bonding. There's ionic bonding. There is which are simply electrostatic attractions between ions. There's covalent bonding, where sharing of electrons is involved in a molecule. And there's also metallic bonding. Now, I didn't talk about this in Honors Chem last year, but maybe some of the other teachers did. But basically what happens in a metal, let's say you have a sheet of iron, is you have you have the nuclei lined up. You have atoms sort of in a crystal lattice, just like they would be in a solid. But the electrons that go with those are mobile. They're called a sea of electrons. They don't stay with their own specific nucleus. And this fact that these electrons are able to move is what allows metals to be electrically conductive. And also heat conductive. Okay, so we call that a sea of electrons. That's a term that might come up in the AP test. So three types of bonding: ionic, covalent, and metallic. And metallic just refers to a metal bonding with itself. So you know ionic bonding, right? So let's say you have a sodium atom, and this sodium has 11 electrons, and it's got just one in its valence shell. It's going to give up that electron so that it loses that outer shell, and it only has 10, 8 in the outer shell. It becomes nice and stable, loses an electron along with some energy. And then there's a corresponding chloride atom that has 7 in its outer shell, 7 electrons in its valence shell, and it wants to pick up an electron in order to also become more stable, to get a full stable noble gas configuration. And so the sodium loses an electron and the chloride gains an electron. It becomes a full positive and a full negative charge. And then what holds these together in the crystal lattice is this full electrostatic charge, plus charge on the sodium, minus charge on the chlorine, holding them to each other. If we remember back in thermodynamics, we said that or even in our periodic table lesson, we talked about ionization energy, and we said it takes 495 kilojoules to remove an electron from sodium. So it takes energy to remove these electrons, and even though it's close to the octet and it becomes more stable, it still takes energy to remove them. And we also saw that chlorine, when chlorine gains an electron because of its electron affinity, it loses energy and becomes more stable, so it loses energy here. But yet if you look at this reaction, and let's actually watch a little video of this reaction. Let me see if I can turn off my arrow options, okay. Or not. I want an arrow. Visible arrow. Alright. So if I look at this little video here, now I've got 3 of them up. Okay. Alright, so let me play this.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
Okay, so when we look at that, what we see is a really exothermic reaction, and the question is, why is it so exothermic, this coming together of this crystal? And the third piece of the puzzle, besides the energy taken to take an electron away from sodium, or the energy lost when chlorine adds an electron, it's this whole lattice energy. So lattice energy is the energy required to completely separate a mole of a solid ionic compound into gaseous ions. So the reverse of that is the energy that's lost when the ions come together to form a lattice. So it's this big reduction in energy because this lattice is very stable, very low in energy. So this lattice energy is the third piece of the energy puzzle that results, in this case, in a very exothermic reaction when we make this ionic compound or salt. So let's take a look at lattice energy. So again, these are energies required to separate the ionic compound in the lattice and make these go off as a gas. So let's take a look. We've got a bunch of ionic compounds, and we have kilojoules per mole of energy required to break those apart. So what do we notice? What are some of the trends you might see? Well, one of the things you should see is all of these ionic compounds have a positive ion that's a +1 and a negative ion that's a -1. And what we have here is a positive ion of +2 with a -1. Here it's a +2 with a -2. And here we have a +3 with a -3. And what we see is as we go from a +1, -1, and increase the charge, the lattice energy goes up. So the stronger the charge of the ions, the closer held those ions are to each other. Okay, so here when we have +3, -3, have the greatest energy of all. Now the other thing we can look at is we can look at, let's say, lithium chloride, fluoride, and iodide. So if we look at fluorine, chlorine, and iodide, as we go down this row or this group in the periodic table, what's happening here is this ion is getting larger, right? I'm adding another shell. These are getting larger. So the distance between the lithium nucleus and the chlorine nucleus are further apart. So they're less tightly held. So it's less energy for a larger ion than it is for a smaller ion. So the smaller, as you can imagine, the more those nuclei in the charges get involved in holding that lattice together. But the biggest impact is the impact on the charges. So lattice energy increases with two things. The first and most important is the increased charge of the ions, and the second thing is decreasing size of the ions. So this energy is associated with Coulomb's law. If you remember electrostatic energy, there's some constant, and it's Q1, Q2. Those are the charges, right? Charge on the positive, charge on the negative, divided by D, which is the distance between them. Okay, so this is why, if this is a +1, -1, this is going to be a smaller electrostatic energy than if this was a +2, -2, right? Okay, so let's take a look and try to apply this. So we have sodium fluoride, cesium iodide, and calcium oxide. So let's first look at the charge, because the charge itself is enough to make a difference. So I want to get my pointer working here. I have in this case, a +1, -1, +1, -1, +2, -2. So this will be the strongest, right? This is the highest. And here I have, these are both +1, -1. So let's take a look at the comparison of the ion size. So sodium fluoride compared to cesium iodide. Cesium is bigger, right? Sodium is smaller. And iodide is also bigger compared to fluorine. So this is going to be higher than the cesium iodide. So this would be the lowest, second lowest, third lowest or highest. Okay, let's take a look at these. So this is a +2 with a -1, a +2 with a -1, a +2, and a -2. So this is going to be the highest right here. And if I compare these, both have fluorine, but there's a difference between magnesium and calcium. So magnesium is smaller, calcium has another shell. So this is going to be stronger, so it's going to be 1, 2, and 3. Okay, so in covalent bonds, atoms share electrons, and there are several interactions. There are attractions between the electrons and the nucleus. There's repulsion between electrons, and there's repulsion between nuclei. So let me just, let me go back and take a look at that little animation. And I want to look at the bond formation.
When two hydrogen atoms approach one another, weak attractive forces operate between them. As they approach more closely, their 1s orbitals overlap more extensively, and covalent bond formation occurs. As the atoms move still closer together, the electron pair that forms the bonds does not effectively screen the nuclei from one another, and nuclear-nuclear repulsion becomes more important. The minimum energy structure in which the nuclei are separated by 0.74 angstroms corresponds to the best compromise between nuclear repulsions and the attractive interactions between the electrons and the two nuclei.
Okay, so there's a perfect distance, there's a sweet spot where the energy is lowest. As the atoms are further apart, the energy will go down as they come together and the electrons come together in the bond. But if they come too close, then the two positive nuclei have repulsion for each other, causing the energy to go back up. So it's all about finding the sweet spot where the one nuclei is attracted to the electrons from the other atom and vice versa. And that's where you have bond formation. Okay. Now, electrons are not always equally shared. As you know, if I take fluorine and hydrogen and I make hydrogen fluoride, we know that the fluorine is more electronegative than the hydrogen. So the fluorine is going to pull harder on that pair of electrons than the hydrogen will. And what we say forms is a dipole. And we draw the dipole like this. We would draw an arrow. And the more negative side would have the head of the arrow. And we put a little plus at the end. It's almost like this is the more positive side. It becomes like a little plus sign. So we would indicate a dipole here. There's no dipole here in the fluorine. They share equally. Okay? So this is going to become a polar molecule. There's more electron density here where the fluorine is because it's going to pull more on those electrons. And it's all governed by electronegativity, right? So if you remember, the most electronegative element is fluorine. It's a very high Zeph. As I go across, I'm increasing the effective nuclear charge. At the same time, I'm adding electrons. Okay? And as I go down a group, I'm getting more shielding of that Zeph or that electron or that nuclear pull as I add more shells. So remember those trends, because the higher the electronegativity, the more that atom is going to pull on the electrons, therefore making it more polar. Okay, so it's the difference in electronegativity that determines, in a bond, that determines whether or not a bond is polar. So as you remember, from left to right, electronegativity goes up, and from the bottom to the top it goes up. So if you think about fluorine is the high, it goes down from there both ways. So when atoms share electrons unequally, we call that a bond dipole. One's more positive, one's more negative. There's some distance between them. There's actually a way to calculate what's called a dipole moment. It's got a value of U, and it's produced by unequal charges separated by a distance. Now we're not going to actually calculate these, but you do need to be able to compare the differences in the dipole moments based on differences in electronegativity. So the greater the difference in electronegativity, as you can see, the highest electronegativity has the highest dipole moment. Okay, so the greater this is, right? And these would be, you could draw these as a shorter arrow than you would here. Okay. Now what you'll see is higher electronegativity difference, higher dipole moment, in shorter bond length, and that's because those electrons are being pulled tighter in, making the bond shorter. So the lower the electronegativity difference, the larger the bond, the further away the electrons or the two nuclei in the atoms are. Okay, so all these three things go together, and you need to understand their relationships. Alright, so in order to determine which bond is more polar, we need to look at the table of electronegativities. In general, when you get asked questions on the AP exam, you'll need to use the trends. But if you wanted to compare exact differences, you can use a table of electronegativities. Okay, so if I look at boron chloride versus carbon chloride, I have boron is 2, has a value of 2. Chlorine has a value of 3, so the difference here is 1. Carbon has a value of 2.5. Chlorine has a value of 3. This difference is 0.5. So the greater difference is boron and chlorine. So that's going to be more polar. If I look at PF versus PCl, so here's F, here's Cl, here's P. It's going to be obvious that it's going to be F because it's further away from the P than the Cl is. But if I actually put numbers to it, P would be 2.2 for both. Whoops. F is 4. Chlorine is 3. So this is going to be 1.8. Or, let me see. Was that a 2.2? 1.8? This is going to be 0.8. Okay. So the PF is going to be more polar. So we need to be able to draw Lewis structures on the test. It gets asked a lot in the free response section. And the Lewis structures are representations that show all electrons both bonding and non-bonding. So we need to not show just the bonding pairs, but also we need to be able to show the lone pairs on atoms. We've done this a lot in Honors Chem, so my guess is this is old hat for you, but find the sum of the valence electrons in the atom. So phosphorus has 5 valence electrons. Each chlorine, there are 3 of them. Each has 7. That's a total of 26. If this is an ion, let's say it's a sulfate ion, which has a -2 charge, I'd add 2 more electrons. If it's an ammonium ion, which has a positive charge, it means it's lost an electron, and I would subtract 1 electron from the tally. Okay. Now, one of the important concepts here is the central atom is always the least electronegative element that's not hydrogen. Hydrogen can never be central because if I have hydrogen and something else, this hydrogen effectively will have 2 plus 2 or 4 electrons around it, and it can't. You know hydrogen can have no more than 2, so hydrogen is always on the outside. But other than hydrogen, it's always going to be the atom that is least electronegative that's going to be on the outside. Alright, so I want to keep track of the electrons. I've got 7 times 3 is 21, plus 5 is okay, so I've put phosphorus in the center. I've put 3 chlorines on it. They need a bond, so I've used 6 electrons. I have 20 left. So now you can draw these as dots, which is the preferred way. If you're lazy like me, or if you're just really sloppy like me, you can actually do this and get away with it on the AP exam. Okay, so now I'm giving everybody that's not part of the, that's on the outside, a full octet. So I have 8, 8, 8, and 8, and I want to see if I've used the right number of electrons. So I had a total of 26. which means 13 pairs. So I've got 4, 8, 12, 13. I had 26 electrons. That's 13 pairs. So this structure is good. It looks kind of messy, but it's a good structure. So we filled the octets of the atoms. We kept track of what we had left. We had another pair for the central atom. We put those there. Okay. So if you run out before the before the central atom has an octet, then you're going to need multiple bonds. So let me just count here. We have H, C, N. Hydrogen is 1. Chlorine has 4 valence electrons. Nitrogen has 5. That's going to be a total of 6. So I've got 2, 4, 6, 8, 10 electrons. Nitrogen's happy because it's got 8. Hydrogen's happy because it's got 2. But carbon only has 2, 4 electrons. So I have to take one of these pairs, eliminate from there, and put it here. Now this carbon has 2, 4, 6. Doesn't have enough, so I've got to take another lone pair and move it here. So now this carbon has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8, and everybody's happy. Now we've got to form multiple bonds, and when we do that, the thing you got to keep in mind is there's only 5 atoms that will 5 elements that will form multiple bonds, and they are known as the CNOPs: carbon, nitrogen, oxygen, phosphorus, and sulfur. The CNOPs. Okay. Now this is a step that we did not do previously in Honors Chem, and what you'll find sometimes is there's more than one possible Lewis structure. So for instance, if I take CO2, there are 2 possible structures, because carbon is 4, oxygen is 2, and there's 6 each. That's 12 plus 4 is 16. And if I arrange them, I can come up with 2 different structures. Okay? So the idea with formal charge is you want to look at the structures you come up with and compare them. So let's just compare them the way that the rules say we compare them, and then we'll talk about what the results mean. So I first start off by listing the valence electrons. Oxygen has 6 valence electrons. Normally, this is when it's not in a bond. Carbon has 4, oxygen has 6, right? Same for both. Okay? Now, if I look at electrons assigned to the atom, I've got to count any lone electrons that are on that atom alone, plus if they're in a bond, I take half of those 2. So I've got 1 here and 1 here, that's 2, 4, and 6. So I also have 6 electrons assigned. Carbon, I have no lone electrons, but I have 1, 2, 3, 4. 1 each from these 4 bonds, that's 4. The oxygen, I have 2, 4, 5, 6. So if I look at the difference between the valence electrons for the atom by itself, and I subtract from that electrons assigned in this structure, I get formal charges of 0, 0, 0. Okay? As opposed to if I looked at this structure where I have 1 single bond and 1 triple, now I have this oxygen has 2, 4, 6, 7 electrons assigned, which gives it the difference between the 6 it normally has as an atom and the 7 assigned here. It gives me a -1. The carbon has a 1, 2, 3, 4 formal charge, which is okay, and the oxygen has 2, 3, 4, 5, which gives it a +1. Okay? So when we do that, the rule is if you have a structure where the formal charges are all 0, that's your preferred structure. Okay? And the second rule that we'll look at a little bit more in detail is if you end up with 2, let's say you have 2 situations where they both come out with a charge, what you want to make sure is the most negative of these belongs to the most electronegative of the atoms. So we'll look at an example with that. Alright, so if we look at, here's the example. So if we were to do the formal charge, let's just do it for practice. 2, 4, 6 plus 1 is 7. You should do this by yourself first. So nitrogen, so I'm going to pause, okay, and then you come back when you're done. Alright, welcome back. So nitrogen normally has 5, carbon has 4, oxygen has 6. 5, 4, and 6, 5, 4, and 6. With this structure, with a single and a triple, oxygen has 2, 4, 6, 7, which gives it a -2. Carbon has 1, 2, 3, 4, which makes it okay. Oxygen has 2, 3, 4, 5, which gives it a +1. Now you want the charge on this whole thing to end up being the charge of this ion, which is -1. And this comes out to be -1. But let's take a look at this. 2, 4, 5, 6. This makes it a +1. I'm sorry, this makes it a -1. Carbon has 1, 2, 3, 4, which is 0. Oxygen has 2, 4, 5, 6, which is also 0. So this also comes out in total as a -1, matches here, just like this did, came out -1, and it matches. Now nitrogen here has 2, 3, 4, 5. Okay, carbon has 1, 2, 3, 4, 0, 0. And oxygen here has 2, 4, 6, 7, which gives us a -1. Okay, so these all come out to be -1. So now we want to look at that the -1 belongs to the atom that's least electronegative. So if I look at my periodic table, oxygen is more electronegative than nitrogen, and carbon is less electronegative than nitrogen. So you want the most electronegative atom to have the negative charge, and in fact this would be the preferred structure, because you want the oxygen to have a -1. Okay, so that's how formal charge works. Okay, so you should be able to do a whole bunch of Lewis structures. If you need practice with that, I can give you some worksheets for those back from Chem 1. Just let me know. So let's try drawing the Lewis structure for ozone. So I have 3 oxygens, each has 6 valence electrons, that's 18. So I'm going to, the only thing I really can do is line them up. I'm going to give everybody an octet. When I do that, I have 8, 16, 18, 20. So I've got too many electrons, so I need a double bond. So I'm going to redraw this. So this is the structure for ozone. Now, I could have drawn that one of 2 ways. I could have drawn it like this. Whoops. Let me make them a line so it's obvious where I've done this. I'm going to put the double bond on either side. And you could argue that this is the same, because if I just flip this, they're always rotating in space, that it's the same thing. But what you would expect then is that this is a symmetrical molecule, that the bond length here is the same, is going to be less than the bond length here. But as it turns out, that's not the case. As it turns out, data shows that the bond length for both bonds is exactly the same, and that in fact it's a symmetrical molecule. So that what that says is that this bond, this is not quite what it looks like. That what it really looks like is some hybrid of this, where this second bond is moving. It's mobile. It's delocalized. Okay. So we call these resonance structures. So here we have ozone. And we put a bracket around it and say it could be that, or this is a proper way to show resonance structures. And in fact, they are some amalgam of the two. So we use multiple structures to describe the molecule. We can't describe it with any one of those, and we put the brackets on to show that they are resonance structures. So just as green is a synthesis of blue and yellow, ozone is a synthesis of the 2 resonance structures. In fact, these bonds are identical based on all the data scientists can put together on those. Okay. Okay. So what scientists say is this second bond here that made the double is really, it's mobile. It's not localized, it's delocalized. Okay. Another popular substance, which you should know benzene. It's one of those compounds that does not go by its IUPAC name, but it's a very common structure that gets used a lot in examples. It's actually a carcinogen. We used to use it to clean out. It was a really good solvent. We used to use it to clean out dirty paint tanks. And I actually have some good friends who died from leukemia, and we suspect it's from benzene exposure. But the structure is, it's a C6H6, and if you build that, what you'll find is that we have 6 times 4 is 24, plus 6 is 30. Each of these has a hydrogen on the outside. 1, 2, 3, 4, 5, 6, and that I don't have enough electrons to give all these carbons a full octet. So what I end up needing is 3 double bonds. So it alternates double bonds. So you could argue whether it's the double bond is here or here. In fact, benzene is often written with this shortcut. And what you see when you look at the structure of benzene, scientists look at it, is it's this. It really does look like a ring structure with the electrons forming this circular pattern. So the electrons are delocalized, they move. Okay. So let's take a look. Let's predict which of these are going to have shorter sulfur-oxygen bonds. So I have SO3. Let's draw the Lewis structure. SO3, that's 6 from sulfur plus 3 times 6 from oxygen. That's going to be 18 plus 6 is 24. So I have SOO. I'll do it like this. And give everybody an octet. If I do that, I have 8, 16, 24, 26. I have too many, so I'm going to make a multiple bond. And if I do that, then I really need to draw 3 structures because this is a resonance, right? And the double bond could be on any of those. Oops, that one's not there. Let me use my eraser and erase that. I'm gonna move to my lines because I am really sloppy, as you can tell. Okay, so this is SO3, right? It's a resonance structure. Now let's for SO3 minus 2. So it's going to be the same electron count plus 2 electrons. So if I do that, that was the original structure I had when I had full octet everywhere, right? And I have 8, 16, 24, 26. So I don't need multiple bonds here. And this is a minus 2. So here's the deal. So which has shorter bonds? So if I have a single, a double, and a triple bond, the triple bond is going to pull those atoms the closest together because I have greater electron density pulling on that. If I have a double bond, it's going to, I'm doing this wrong. If I have a single bond, it's going to be like that. Double bond is going to move them in closer. Triple bond, really high electron density between them is going to move them really close. So the more electron density in between the two nuclei, the closer those bonds are going to be, the atoms are going to be pulled. So the bond length gets shorter as I add a multiple bond. So here I have all single bonds. Here I have singles and doubles. So remember, these three bonds are really sort of an amalgam of the three. So the bond length is going to be a little longer than the single bond, but a little shorter than the double bond. So the shortest bond length is going to be my SO3, because I have no multiple bonds here. Alright, so let's draw two equivalent structures for the formate ion. So I have carbon, so at least the electronegative is going to be in the center, O and O, C, O, O, H. And I have 1 electron, 4 electrons, 6 electrons, and this is 1 electron. So it's 12 electrons. So I have 2, 4, 6, 8, 10, 12, 14, whoops. Let me see. Whoops. This is my problem. I have 6 plus 6 is 12, so that's going to be 18. Alright, that's 12 plus 4, yeah, 18. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so I need a double bond, and I'm going to take them away from there and put them here. I'm also going to do the same thing over here, because this is resonance, right? And then I put my lone pairs to give everybody a full octet, and that should do it. Okay, these are resonance, so I put them in brackets. Okay, so here are some exceptions to the octet rule. This is something we did not talk about in Honors Chem. So there are 3 types of situations where we have exceptions. One is where I have an ion or a molecule that ends up with an odd number of electrons. It doesn't happen much, but it does. Ions or molecules with less than a full octet, and ions or molecules with more than 8 valence electrons, an expanded octet around the central atom. Let's take a look at them one at a time. So these are rare. Odd numbers of electrons. Here I have nitrogen monoxide, and it ends up with an odd number of electrons. Very rare, very unstable. Don't get asked much about this on the AP test. Now, I also have situations where I end up with fewer than 8 electrons. And if I do the formal charge thing, I end up with a negative charge on the central atom, which is never a good situation. So the other option is to end up with a neutral charge on the central atom, and a neutral formal charge, and have less than a full octet. Now, where you find less than a full octet is small atoms. Okay, so if you look at where boron is, it's row 2, period 2, and it's got 3 valence electrons. So it's very small. So it kind of rationalizes that a small atom sometimes can't fit all 8. Okay, kind of a weak explanation, but that's the wisdom people use. Okay, so if you remember CNOPS, which is which atoms form double bonds, fluorine's not part of that group, so this is not a good structure. Okay, so for a couple of reasons we're going to know it's that. And more common is where you have an expanded octet. You have a central atom that ends up with more than 8 electrons, 2, 4, 6, 8, 10. And that does happen more commonly than the other 2 exceptions. So the only way PCl5 can go together is to have 10 electrons around it. Now, the only elements that can have an expanded octet are those that have d electrons. So the current wisdom is that you need d orbitals, even if they are unoccupied, that allows for this expanded octet. So that what that means is anything in row 3 or, now here it says 3 or below. So when we say 3 or below, we're talking about below it in the periodic table, not lower than 3 in number, right? So it's got to be at least the 3rd row, and phosphorus is the 3rd row. There are d orbitals here. They're not filled, right? But that's okay. So this only happens when you have an element that can handle an expanded octet, which means it has d orbitals, even if they are empty. Now, even though we could draw a structure where this phosphate ion has a expanded octet, the preferred structure is one where it has a double bond. Okay. Actually, there's 2 structures that work here. What happens here is the phosphorus ends up with a formal charge of +1. You want a formal charge in the center of 0. So here it is, everything looks nice and pretty, but here what you have is formal charge becomes 0, and you end up with an expanded octet. 1, 2, 3, 4, 5. Okay. So in the central atom in the 3rd row or below, an expanding octet eliminates some formal charges. And by formal charges, again, we're talking about just that calculation. It's not an actual charge, but it's the formal charge calculation we talked about a couple slides earlier. We want that central atom to have a 0. Alright, so let's try drawing a Lewis structure for ICl4. So I is 7 valence electrons. 4-chlorine is going to be 7 times 4 is 28. That's going to be 35 plus 1 is 36. So if I have I, and I have Cl, 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 and let me put bonds here, and I'm going to draw dashes instead of pairs because I am completely lazy. That means I have 8, 16, 24, 32. I only have 32, I need 36. The only option here is none of these are CNOPs, right? CNOPs. You can't have a double bond with this chlorine. So what I end up having here is an expanded octet. Put my 2 extra electron pairs here. Okay, so which of the following is never found with more than an octet? SC or BR. So let's see, which is at least the 3rd period. Sulfur is, chlorine is not, and bromine is. So it could be with S or BR. Okay? How about XCF2? Kind of a strange one because we have a noble gas. It's got 8. Plus 2 fluorines makes 14, so that's 22. So noble gases do sometimes form compounds. It's rare, but it does happen. So if I have FXE, and I have my F, and I put my... What did I do there? That's just an F. Okay. And I end up with 8, 16, 18, 20. The only way this is going to work is if I put an expanded octet here. Okay? That's what has to happen. It's a big boy. You can do it. It's in more than the 3rd period. It's in the 5th period. Alright. So we can look at covalent bond strength. And bond strength is a measure of how much energy is required to break a bond. Now we talked about some of this when we talked about enthalpy in the thermochem section. So bond strength is listed as the energy required to break a bond, so it's always a positive value. It's called bond enthalpy because it always takes energy to break a bond. So if I look it up on the table, and I think I've given you a table earlier, 242 kilojoules to break this bond. Always positive. Always requires energy to break a bond. Okay? So energy must always be added to break a bond. Okay? All these values, therefore, are positive. And what you will see if you compare is a C bond. Let me see. I know this one here is 348 kilojoules. Double bond 614. Triple bond even more. So higher electron density in here causes the bond to be much stronger, pulling this closer together, like 3 bungee cords instead of 2. So multiple bonds are stronger bonds. Now, if you look at enthalpies of a reaction, and again, we did this enthalpy calculation, the change in enthalpy in this reaction, you can look at bonds broken minus bonds formed. Now, this gets a little confusing because it's always products minus reactants when we did the change in enthalpy before. What you need to know is bonds breaking always is positive energy, and bonds being formed is always a negative energy. Okay? So in order for this reaction to occur, I need to break the bonds between the Cl and the Cl and the C and the H. And that is endothermic, requires a bunch of energy. But when these come back together, okay, these bonds are formed, that releases energy. And if the net is a greater release, then this is going to be exothermic, right? But bond breaking, first step, always requires energy. Bond formation always releases energy. And you don't know whether it's exothermic or endothermic depending on the difference in the height and where these end up. Okay, but you do know bonds broken, positive, bonds formed is negative, and the net tells you what the change in enthalpy is. Okay, so I can look these up in that table I gave you. So I gotta look at breaking the 4. Let me see. I have I have 4 CH bonds. I have 1 Cl bond. Both of those are going to require energy. It's going to be energy and energy. And I'm going to get out energy and energy. I'm going to add them all together and see what I get. Okay? Look these up on the table. And I get this. Bond length is closely related to bond energy. The higher the bond energy, the lower the length. These are close together. You know, lots of bungee cords pull these close together compared to these, a little further apart. And it all has to do with the pull of these electrons with the nuclei. The more electron density here, the more they're going to pull, and the closer together they're going to be. Okay, so a big bond length is generally more associated with a low bond energy, right? It's further apart because it's not being pulled too closely together. Okay, so the bond length decreases as the number of bonds increases. And we're going to stop there.